Okay, everyone, welcome to today's live stream. So I feel that it is better to talk about some fundamentals before actually diving into some real algorithms. So basically, here we are today. I'm gonna walk you through the introduction section, some important concepts in the introduction section of pattern recognition machine learning. So we're going to read through this together in today's live stream and see how much we can go through. Okay. So polynomial curve fitting. Should we turn this a little bit bigger? So we begin by introducing a simple regression problem, which we shall use a running example throughout this chapter to motivate a number of key concepts. Suppose we observe a real valued input variable x, and we wish to use this observation to predict the value of a real valued target variable t. Okay. So what does it mean by regression? Regression problem is basically that when the output of the machine learning model is continuous, okay, rather than discrete. For the present purposes, it is instructive to consider an artificial example using synthetically generated data, okay, because we then know the precise process that generated data for comparison against any learned model. The data for this example is generated from the function sine 2 pi x, with random noise included in the target values. Okay. Now suppose that we are given a training set comprising n observations of x, written as x is composed of n occurrences, okay, together with corresponding observations of the values of t. Okay, so you can basically think about the input and the label. So figure 1.2 shows a plot of training set comprising of 10 data points. 1.2, basically that each circle here is a data point or an observation. The input data x, the input data set x in figure 1.2 was generated by choosing values of xn, okay, spaced uniformly in range 0 to 1 closed interval, okay? So basically you just sample here. And target data set T was obtained by first computing the corresponding values of the function sine 2 pi x, and then adding a small level of random noise following the Gaussian distribution, okay, to each such point in order to obtain the corresponding value Tn, okay. So you basically you can see a kind of pattern here, right? This is x-axis. Okay, and this is the second axis, okay? And this trend here, overall trend follows sine 2 pi x with a little bit Gaussian noise. By generating the data this way, we are capturing a property of many real data sets, namely that the possesses underlying regularity, which we wish to learn, but that individual observations are corrupted by random noise. Okay, so our goal is to kind of get rid of the effect of random noise and capture the real patterns underneath. Okay, This noise might arise from intrinsically stochastic processes, such as radioactive decay, but more typically is due to there being sources of variability that are themselves unobserved. Okay, our goal is to exploit this training set in order to make predictions of the value t hat of the target variable for some new value x hat. Okay, of the input variable. As we shall see later, this involves implicitly trying to discover the underlying function sine 2 pi x. This is intrinsically a different problem as we have to generalize from a finite data set, because we only have a few observations, right? We want to capture this pattern or this mapping underneath, which is very difficult. Furthermore, the observed data are corrupted with noise, and so far a given x hat, there is uncertainty as to the appropriate value for t hat. Probability theory discussed in section 1.2 provides a framework for expressing such uncertainty in a precise and quantitative manner. And decision theory discussed in section 1.5 allows us to exploit this probabilistic representation in order to make predictions that are optimal according to appropriate criteria. So for less technical content here, I'm gonna speed up my reading pace because the goal is to spend more time actually talking about those more technical concepts and content, okay? For the moment, however, we shall proceed rather informally and consider a simple approach based on curve fitting. In particular, we shall fit the data using a polynomial function of the form. So basically, is that you have an input x, okay? Right now, it's kind of a one-dimensional input space, and you want to kind of feed some polynomial curve function to generate its prediction. And the form is going to look like this. Form is going to look like this. So it has this kind of zero orders term, first order term, second order term, blah, blah, all the way until the highest order term, okay? And m is actually the order of the polynomial, and xj denotes x raised to the power of j. Okay, it's not kind of a, it's superscript in the sense that it actually denotes the power, okay, rather than an index. The polynomial coefficients, okay, W0 all the way to Wm, so zero's order all the way to m's order, are collectively denoted by the vector W. Okay, so W is going to be W0, W1 all the way to W. And so it's going to, Wm. It's going to be m plus 1 dimensional vector. Okay. Note that although the polynomial function is a nonlinear function of x, it is a linear function of the coefficients W. Okay. So if we look at it, why do we say that? Why do we say that? So at x, you take a lot of high orders, right? But for W, so this polynomial, if you write it in a vector form, is actually x, so 1, x, x2, all the way x, m. Dot product with W0, W1, all the way to Wm. Okay, so x, we only have one element of it, and we are taking different orders to produce different elements. But for W, we already have m plus 1 elements. So we don't take like a nonlinear transformation of W. Basically, it's just a single linear dot product that produces the real the actual output. So it's actually a linear function of the coefficient W. Okay. Functions such as polynomial, which are linear in the unknown parameters, like the general convention is that when we say linear, nonlinear, okay, it's with respect to the with respect to the weight parameters, okay, have important properties and are called linear models. Let's read this sentence again. Okay, this is important one. Functions such as the polynomial, which are linear in the unknown parameters, have important properties and are called linear models. Okay, so the definition for linear models is actually with respect to the parameters. Okay, to the parameters rather than the input. Okay, rather than X in this case. Although X is transformed to higher orders, okay, it seems that X is transformed in a non-linear manner in this case, but the linearity here, when we refer to it, we are talking about the linearity with respect to the weight parameters. Okay, and in that case, if it is linear in the sense that weight parameters are linear, okay, then we call it linear models. And yeah, basically this will be discussed extensively in later chapters. The values of the coefficients will be determined by fitting the polynomial to the training data. This can be done by minimizing an error function, okay? Note down this keyword that measures the misfit between the function yxw for any given value w and the training set data points. One simple choice of error function which is badly used is given by the sum of squared errors between, it's important here, okay, between the predictions y, x, and w. So y, x, and w here is actually referring to the function output given the input xn and the weight parameters, okay, for each data point xn and the corresponding target values tn, so that we minimize the sum of the squared errors. Okay. So here the sum, as we can see, is in terms of the capital N data points or observations. Okay, and the square here is with respect to the errors or the differences between the predictions and the true and the true labels. Okay, where the factor is included, whether factor 1 or 2, 0.5 is included for the convenience of taking the derivative later on. Okay. We shall discuss the motivation for this choice of error function later in this chapter. For the moment, we simply know that it is a non-negative quantity that would be 0 if and only if the function mapping that we fit, okay, which is represented by y given x and w, were to pass exactly through each training data point, which is called a perfect fit, right? The geometric interpretation of the sum of squares error function is illustrated in 1.3 here, okay? Let's take a look. The error function corresponds to sum of squares of the displacement of each data point from a function y given x and w. Okay. Suppose basically like suppose this this is something that we learn, okay, which is y given x and w, and the circles here are the labels, basically that we are just calculating the sum of square of errors. Okay. We can solve the curve fitting problem by choosing the value of w for which EW is as small as possible. Okay, we want to choose something that gives us as small error as possible because the error function is a quadratic function of the coefficients w. Okay. So quadratic in the sense that quadratic with respect to w because there's a square term here, right? Its derivative with respect to the coefficients will be linear in the elements of w. Okay, its derivatives with respect to the coefficients will be linear in the elements of w. Okay, so the minimization of the error function has a unique solution denoted by w star. Okay, which can be found in closed form. The resulting polynomial is given by the function this. There remains the problem choosing the order m of the polynomial. Okay, so this is something that's gonna be manually chosen. Okay. As we shall see, this will turn out to be an example of important concept of model comparison or model selection. So in figure 1.4, we show 4 examples of the results fitting polynomials having orders 0, 1, 3, and 9 to the data set, showing in 1.2. Okay. So let's see where is 1.4. Okay. So when we fit a order 0 polynomial, okay, then it's basically a constant, right? It's basically a constant. So you're just moving kind of a straight line up and down to fit the data points. And apparently you can't really fit the data points really well, right? And so this is m equals to 0. And the second case is m equals to 1. What this means is that you can have a slope, right? You can not only have a up and down position, but you can also have a slope. Okay. In that case, you can see maybe it's fitting the data points a little bit better. And the third example given is actually m equals to 3. And basically the highest order here is actually x cubed, right? So in that sense, we can see that it's fitting the data points much better compared to the previous 2 examples. So this one, great. Okay. And if we set m to be a very high order thing, say equals to 9, and it tends to fit the data perfectly, but it's kind of, over exaggerated what is the pattern underneath, right? So in this case, it not only fits the data, but it's kind of giving some unnecessary behaviors. So let's see. Those few examples actually point out to some very important perspectives, namely underfitting and overfitting in machine learning. And if you look at kind of machine learning research, a large set of research papers are, kind of dealing with these important concepts. So, okay, let's keep reading here. We notice that the constant and first order polynomials give rather poor fits to the data. And consequently, let's change the color here. These two give very poor fits to the data and rather poor representations of the function sine 2πx. Okay. Differently, the third order polynomial seems to give the best fit to the function sine 2πx. Okay. And when we go to a much higher order polynomial, we obtain an excellent fit to the training data. Not important here. Okay, the most important thing is that is the however part. So when you talk to somebody, okay, when you write something down, when you actually say something, oh, this thing is good, but this thing is good, however, okay, actually, but what comes after however is something that you mostly need to pay attention to. Okay, so here, however, the fitted curve oscillates wildly and gives a very poor representation of the function sine 2πx. So in this sense, we already know that the ground truth is actually sine 2πx. So as I have pointed out previously, this fitting here actually kind of over-exaggerated what should be the behavior underneath. Okay. And this later behavior is known as something called overfitting. Okay. Again, a large set of machine learning research, they are dealing with this problem called overfitting. So it's very important that you get an idea of what overfitting looks like when you firstly get exposed to machine learning, and later on, okay, as we talk about more concepts, you can get a better sense of what overfitting really is. So, as we have noted earlier, the goal is to achieve good generalization by making accurate predictions for the new data. We can obtain some quantitative insights into the dependence of the generalization performance on M by considering a separate test set comprising 100 data points. So here, the authors try to bring us to another important concept, which is called test set. Let's see if he explicitly mentions this or not. If not here, then maybe he's then he is mentioning this in the later part of the book. Okay. By considering a separate test set comprising 100 data points generated using exactly the same procedure used to generate the training set points, but with new choices for the random noise values included in the target values. Okay. For each choice M, we can then evaluate the residual value of W star. W star, remember that W star, what is W star? We just mentioned this. The minimization, let's quickly recap this. Okay, the minimization of the error function has a unique solution denoted by W star. So you can think about it as the minimum of your error function. Okay. In the case of a parabola, okay, it's the lowest point there. Okay. We can also evaluate for the test data set. Okay. Again, test data set is something that it is independent from your training data set, which is used to test your function mapping learned. Okay. Separate test set comprising 100 data points. It is sometimes more convenient to use the root mean squared error, okay, defined by root mean square error. What does it mean? Okay, there are two important terms here. Do you notice that? What is that? Root. Okay. Another thing is mean. Okay. So you're averaging the error, okay, by the number of observations or the number of data points, and then you take the square root of it, okay, which is called root mean square error, in which the division by n, okay, allows us to compare different sizes of data sets on an equal footing. And the square root ensures that root mean squared error is measured on the same scale as the target variable t. Graphs of the training and test set are of root mean square errors are shown for various values of m in figure 1.5. The test set error is a measure of how well we are doing in predicting the values of t for new data observations VAX. We note from figure 1.5 that small values of m give relatively large values of the test set error, and this can be attributed to the fact that the corresponding polynomials are rather inflexible and incapable. Notice the word incapable, okay, of capturing the oscillations in the function mapping sin 2πx. Okay, so basically that doesn't have enough capacity to capture the underlying pattern. Values of m in the range of 3 to 8 give small values for the test error. These also give reasonable representations of the generating functions sin 2πx, as can be seen, okay, from 1.4, right? So here, let's look at this figure 1.5, which is really, really good. So when we gradually increase m, okay, and the test error firstly go down, okay, and then it kind of get increased at some certain point. Okay, so for this part, you can actually regarding it as underfitting. Okay, which basically means that your model is not capable enough to capture the pattern shown by the data, okay, given by the data. However, if you keep, increase the model complexity to some certain point, here, you perfectly fit the training data, but in this part, you're not fitting well on the testing data. And this is something called overfitting. if you read a lot of representation learning papers, overfitting is basically something that you not only capture the pattern in the input data, but also capture a lot of training data set noise. Okay. So the goal of representation learning is basically to retrieve the patterns or retrieve the useful information from the input data and get rid of noise as much as possible. Okay, reserve as much as useful information, get rid of as much as useless information. So here, in the case of overfitting, it is kind of reserving both useful and useless information. Okay, so for the case of underfitting, it is not even capable to reserve the useful information, not to mention the useless information. Okay, because the model is simply too simple. So for m equals to 9, the training set error goes to 0, as we might expect, because this polynomial contains 10 degrees of freedom corresponding to the 10 coefficients. So can be turned exactly to the 10 data points in the training set. However, the test set error becomes very large, as we saw, and the corresponding function exhibits wild as oscillation. So it becomes too exaggerated, right? Even much more exaggerated than it should be. Okay. So this may seem paradoxical because a polynomial of given order contains all lower order polynomials as special cases. M equals to 9 polynomial is therefore capable of generating results at least as good as the M equals 3 polynomial. Furthermore, we might suppose that best predictor of new data would be the function sin 2pax from which the data was generated. And we shall see later that this is indeed the case. We know that a power series expansion of function sin 2pax contains terms of all orders. So we might expect that results should improve monotonically as we increase m. Okay, let's read this paragraph again. This may seem paradoxical because a polynomial of given order contains all lower order polynomials as special cases. Okay. M equals 3 polynomial is therefore capable of generating results at least as good as M equals 3 polynomial. Okay. So basically, you can think about that way, right? Our intuition tells us that M equals to 9 is at least as capable as the M equals to 3 polynomial. Okay. So in our impression, it should perform better, right? But it's actually not. Furthermore, we might suppose that the best predictor of new data would be the function sin 2pax. Okay, sin 2pax, no doubt, right? It is the ground truth function mapping that generated the data. We know that a power series expansion of the function sin 2pax contains terms of all orders. You all learned this in your calculus class. So we might expect that results should improve monotonically as we increase m. And it's not, right? There seems to be a paradox. I can gain some insight into the problem by examining the values of the coefficient W star obtained from polynomials of various order, as shown in table 1.1. So here is the table. We see that as m increases, the magnitude of coefficients typically gets larger. Okay, let's see. Here is the interest point here. When m equals 0 and m equals 1, okay, the norm of W, it's within some kind of small value range. But when m equals to 6, we observe something as large as this. When m equals to 9, it's kind of going really, really exaggerated, right? In particular, for the m equals to 9 polynomial, the coefficients have become finely tuned to the data by developing large positive and negative values, so that the corresponding polynomial function matches each of the data points exactly. Okay, so exactly is actually the cause of all the problems, but the function mapping is actually trying to do this, right? Increase the scale as much as they want in order to perfectly fit the training data. But between data points, the function exhibits the large oscillations observed in figure 1.4. Okay, so we see that even the ground truth function sine 2 pi x is not fitting the training data perfectly because, you know, there are Gaussian noises we manually added on top of the data points, right? That leave us some deviations from the actual data points between the actual data points and the sine 2 pi x, right? Intuitively, what is happening is that the more flexible polynomials with larger values of m are becoming increasingly tuned to the random noise on the target values. Intuitively, what is happening is that the more flexible polynomials with larger values of m are becoming increasingly tuned to the random noise on the target values. So here is a problem that I just mentioned. It's not only fitting itself to the underlying pattern, but also trying to fit itself to the useless information, which is the Gaussian noise. Okay. It is also interesting to examine the behavior of a given model as the size of the data set is varied, as shown in as shown in figure 1.6. So if you look at 1.6, okay, plots of the solutions obtained by minimizing sum of squares error function using m equals to 9. So right now we fix the order of the polynomial we choose. Okay, m equals to 9. Okay, we just want to be fair. Okay, so we fix the order and increasing the number of data points. So the author uses n equals to 15 and n equals to 100 accordingly. And we see that increasing the size of the data set, reducing the overfit problem. So basically, if you look at the left-hand side graph, okay, so basically you can see that it tries to capture some noise along the way, right? It tries its best to fit the data perfectly. So the end result is that it not only captures the pattern, but also captures the random noise there, right? But increasing the training data set size actually help us alleviate this problem to a large extent, because we can see that when m equals to 9, there is no way for the model to perfectly capture all of the random noises in the training data set, right? So in this case, it sees a larger part of the training data distribution. So it kind of suffers slice from the problem of overfitting, because you see that with n equals to 15 data points, the function mapping that we tries to fit, right, tries to satisfy the needs of every single data point. But for the case of n equals to 100, it still tries to satisfy the needs of every single data point, but it can't at the moment, right? Because the model capacity is limited. It's only m equals to 9 compared to this kind of relatively large data set, which is 100. So instead of trying to perfectly fit every single data point, now it focuses more on capturing the underlying pattern, okay? And as a result, we see something very inspiring, which is that it fits better to the data. For a given model complexity, the overfitting problem becomes less severe as the size of the data set increases. This is a very important problem. So yeah, basically that in the machine learning, okay, if people ask you what are some possible methodologies to reduce overfitting, okay, so one of them that are often widely adopted is actually increase the training data set size, right? Because just think about it, right? We as a person, when we see more things, right, our horizon just expands, and we got better recognition, and our decision tends to get better. When our eye set is not as open as when our eye set is not as open, then we tend to make bad decisions, right? When our eye set opens up, then we got to make better decisions. Same thing for the model, right? It sees limited number of data, then it tends to generate bad decisions, okay? Because it's more biased, right? The model is more biased. But when it's able to see more data, okay, it tends to get a better sense or better overview of what the distribution looks like, and it tends to fit the pattern better. I'm not trying to see fit the data better. I'm trying to see fit the pattern better and make better decisions at the very end. Okay. Another way to say this is that the larger the data set, the more complex the model that we can afford to fit the data. One rough heuristic that is sometimes advocated is that the number of data points should be no less than some multiple of the number of adaptive parameters in the model. Another important sentence here. One rough heuristic that is sometimes advocated is that number of data points should be no less than some multiple of the number of adaptive parameters in the model. However, as we shall see in chapter 3, the number of parameters is not necessarily the most appropriate measure of model complexity. Okay? Keep this sentence in mind, and we will see why it is the case. Also, there is something rather unsatisfying about having to limit the number of parameters in the model according to the size of the available training set. It would seem more reasonable to choose the complexity of the model according to the complexity of the problem being solved. We shall see that the least squares approach to finding the model parameters represents a specific case of maximum likelihood. Another important conclusion here, we shall see that the least squares approach to finding the model parameters represents a specific case of maximum likelihood, discussed in section 1.2.5. And the overfitting problem can be understood as a general property of maximum likelihood. By adopting a Bayesian approach, the overfitting problem can be avoided. We shall see that there is no difficulty from a Bayesian perspective in employing models for which the number of parameters greatly exceeds the number of data points. Indeed, in a Bayesian model, the effective number of parameters adapts automatically to the size of the data set. For the moment, however, it is instructive to continue with the current approach and to consider how in practice we can apply it to data sets of limited size, where we may wish to use relatively complex and flexible models So this is really good book in the sense that it talks about some basic concepts really, really clearly. Even if you're an experienced engineer or scientist in machine learning, right? It's always beneficial for you to go back to review some fundamental concepts because you cannot guarantee yourself in fully understanding the whole ecosystem really, really well, okay? You may already have a very, very good understanding on the majority of the contents, but it's always the case for every one of us. There's something we will meet. Okay. So a good book is worth reading repeatedly. One technique that is often used to control the overfitting phenomenon in such cases is that of regularization, okay? Which involves adding a penalty term to the error function in order to discourage the coefficients from reaching large values. Important concepts, regularization, okay? A bunch of different techniques to it, okay? So there's L1, L2 regularization, right? In the neural network case, there's dropout, okay? A bunch of techniques, and there's is kind of a research area. Also, the very popular data augmentation in the field of computer vision, for example, can also view it as a form of regularization, okay? Which involves adding a penalty term to the error function in order to discourage the coefficients from reaching large values. The simplest such penalty term takes the form of a sum of squares of all the coefficients, leading to a modified error function of the form. You see that apart from just a, square term, okay, sum square error term, there's also another term that actually constrain the scale of the rate parameter. So basically what it means is that if you increase the scale of W, you have to increase the penalty accordingly. The penalty will got increased accordingly, right? So you want to kind of achieve a balance in the sense that you want to get an ideal weight parameter that can help you make predictions in a powerful way, but you also want to constrain the scale of your model parameters to a reasonable size, because either large prediction errors or large weight parameter scales can increase the overall penalty here. Okay. So let's take a 5-minute small break, and I will keep talking about this. Okay. let's continue. So here, it gives you, the author gives you the definition of W square here. Okay, it's basically the sum of square each individual element of the vector W. Okay. Note that often the coefficient W0 is omitted from the regularizer because we don't want to kind of constrain the position of the okay. Because its inclusion causes the results to depend on the choice of origin for the target variable. Or it may be included, but with its own regularization coefficient. Okay. Again, the error function can be minimized exactly in closed form. Techniques such as this are known in the statistics literature as shrinking methods. Okay, because they reduce the value of its coefficients. The particular case of a quadratic regularizer is called ridge regression. Okay, in the context of neural networks, this approach is known as weight decay. Remember this. This quadratic regularizer is called ridge regression. Okay, and in the context of neural networks, this approach is called weight decay. Figure 1.7 shows the results of fitting the polynomial of order m equals to 9 to the same data set as before, but now using the regularized error function. Okay. We see that for a value of log lambda equals to -18, the overfitting has been surprised, and we now obtain a much closer representation of the underlying function, sine 2πx. If, however, we use too large a, so 1.7 is, yeah, it's basically here, right? If lambda is equal to -18, right? We can see that this polynomial curve actually fits the data points relatively well. For a value of log lambda equals to -18, the overfitting has been surprised, and we now obtain much closer representation compared to the underlying function sine 2πx. If, however, we use too large a value for lambda, then we again obtain a perfect, right? As shown in 1.7. Okay, so this can be understood this way. Suppose the parents are educating their child, right? If they don't provide any constraint, then their child will do bad behaviors. But if they give too much constraint, okay, it's also not very good for their child's development. Okay, that's basically the same idea here. We want a moderate level of of kind of a regularization power here. Okay. The impact of the regularization term on the generalization error can be seen by plotting the value of RMS error for both training and test sets against log lambda, as shown here, 1.8. We see that in effect, lambda now controls the effective complexity of the model, and hence determines the degree of overfitting. Okay. The issue of model complexity is an important one and will be discussed at length in section 1.3. Here, we simply note that if we were trying to solve a practical application using this approach of minimizing an error function, we would have to find a way to determine a suitable value for the model complexity. The results above suggest a simple way of achieving this, namely by taking the available data and partitioning it into a training set used to determine the coefficients W in a separate validation set, also called a holdout set, used to optimize the model complexity. In many cases, okay, so here's another important idea, okay? So typically, we have three partitions of the data set when we actually train and test our machine learning model. The first one is called the training set, which is used to train your parameters. And validation set, which is used to tune your hyperparameters. Okay, and the last one is basically the test set. We typically don't have access to it until our model is readily available. Okay. So far, our discussion of polynomial curve fitting has appealed largely to intuition. We now seek a more principled approach to solving problems in pattern recognition by turning to a discussion of probability theory, as well as providing the foundation for nearly all of the subsequent development in this book. It will also give us some important insights into the concepts we have introduced in the context of polynomial curve fitting, and will allow us to extend this to more complicated situations. Okay. So the following part is actually the introduction of probability theory. Okay, kind of not has any. You will typically learn this part in the statistics course. Okay, but it's a very important fundamental knowledge that you kind of want to grasp before you actually learn machine learning. Okay, so I will stop here today, and yeah, see you soon.